March 19, 1945. The steel deck of the USS Franklin shuddered beneath Lieutenant Commander Harold Hank Morrison's feet as another wave crashed against the carrier's hull in the rough seas 60 miles off the coast of Japan. The acrid smell of aviation fuel mixed with salt spray filled his nostrils as he knelt beside the twisted wreckage of what had been a perfectly functional 40mm Bofors anti-aircraft gun just minutes before. The screaming dive of a Mitsubishi A6M0 still echoed in his ears, followed by the thunderous explosion that had torn through the gun mount like tissue paper, leaving 3 American sailors dead and the carrier's portside defenses crippled. In the smoke-filled chaos of that moment, Morrison had no idea that his desperate observation of the kamikaze attack's devastating effectiveness would lead him to develop a revolutionary defensive system that would fundamentally alter the nature of naval warfare, transforming American warships from vulnerable targets into impregnable fortresses that could withstand the most fanatical suicide attacks the Japanese Empire could unleash. The kamikaze threat had evolved into the most terrifying weapon in the Japanese arsenal by the spring of 1945, as the Empire's conventional military forces crumbled under the relentless advance of American naval power across the Pacific theater. What began as isolated incidents of desperate pilots choosing death over surrender had transformed into a systematic campaign of organized suicide attacks that struck at the very heart of American naval superiority. Since October 1944, when the first official kamikaze units launched their attacks during the Battle of Leyte Gulf, Japanese suicide pilots had sunk or damaged over 300 American vessels, killing more than 15,000 sailors and forcing Admiral Chester Nimitz to reconsider fundamental assumptions about naval warfare in the face of an enemy willing to die with absolute certainty to achieve tactical objectives. The statistics painted a terrifying picture of Japanese tactical innovation born from strategic desperation. Kamikaze attacks achieved hit rates exceeding 25%, compared to conventional bombing accuracy rates that rarely exceeded 5% under combat conditions. Each successful kamikaze strike delivered the explosive power of a 500-pound bomb directly into the target vessel's most vulnerable areas, guided by human intelligence that could adapt to defensive measures and exploit tactical weaknesses that mechanical systems could never identify. American naval commanders faced the unprecedented challenge of defending against weapons that could not be deterred by conventional means, as Japanese pilots approached their targets with the absolute certainty of death and the fanatical determination that made evasive maneuvering irrelevant. Morrison, a 1938 graduate of the United States Naval Academy whose mechanical engineering background had earned him assignment to the Pacific Fleet's Damage Control Division, understood naval architecture in ways that formal training alone could never provide. His father had worked the shipyards of Newport News during the Great War, and Morrison had grown up surrounded by the practical knowledge of men who built warships with their own hands. But the kamikaze threat presented challenges that traditional naval engineering had never contemplated. American warships had been designed to withstand conventional attack from bombs, torpedoes, and artillery shells that followed predictable ballistic trajectories, not suicide aircraft that could maneuver until the final moment of impact to exploit defensive weaknesses with human intelligence and fanatic determination. The personal cost of kamikaze attacks had touched Morrison's life with devastating directness. His younger brother Thomas, a gunner's mate aboard the destroyer USS Laffey, had been killed during the massive kamikaze assault off Okinawa just 2 weeks earlier. The official casualty report stated that Thomas had died instantly when a Nakajima Ki-43 Hayabusa crashed directly into his gun position. But Morrison knew the brutal reality that military euphemism could not soften. His brother had faced certain death with nowhere to run, watching the kamikaze pilot's face in the final seconds before impact. That night, alone in his stateroom, Aboard the Franklin, with only the steady rhythm of the ship's engines for comfort, Morrison made a decision that would reshape naval defensive doctrine for generations to come. The breakthrough came to Morrison while examining damage patterns from successful kamikaze attacks across dozens of American vessels that had survived suicide strikes. Working under the harsh fluorescent lights of the Franklin's Damage Control Center, he spent countless hours analyzing photographs, technical reports, and survivor testimonies from ships that had endured kamikaze impacts. What emerged from this systematic investigation was a pattern so fundamental that more conventionally trained naval architects had completely overlooked its significance. Kamikaze aircraft achieved maximum destructive effect by exploiting the geometric vulnerabilities inherent in traditional anti-aircraft gun placement and ammunition storage configurations. Morrison's engineering intuition led him to understand that kamikaze pilots were not merely crashing into American ships at random. They were making calculated decisions in the final seconds of their attacks to maximize damage by targeting specific structural weak points that conventional bombing could never exploit. The human intelligence guiding each suicide aircraft allowed for last-second course corrections that placed explosive impacts precisely where they would cause the most devastating secondary explosions, ammunition detonations, and structural failures. Japanese pilots had transformed their aircraft into guided weapon systems far more accurate and destructive than any conventional bomb or torpedo. The solution Morrison developed challenged every established principle of naval defensive architecture. Instead of concentrating anti-aircraft weapons in traditional gun mounts that created predictable target areas, he proposed a revolutionary defensive system based on distributed, overlapping fields of fire that would eliminate the geometric vulnerabilities kamikaze pilots had learned to exploit. His design called for a network of small, independently operating defensive positions that could provide mutual support while presenting no single critical target that would cripple the ship's overall defensive capability when destroyed. Working through the humid nights of March 1945, Morrison began developing what would become known throughout the Pacific Fleet as the Morrison Defense Grid, or simply Going Distributed. Using technical drawings, mathematical calculations, and scale models built from available materials, he systematically redesigned the defensive architecture of American warships to eliminate the concentrated target areas that made kamikaze attacks so devastatingly effective. The new configuration scattered defensive weapons across the entire vessel in carefully calculated positions that maximized coverage while minimizing vulnerability to single-point failures. The innovation required mathematical precision, combined with practical understanding of human psychology under extreme combat stress. Each defensive position had to be capable of independent operation while maintaining communication with adjacent positions to prevent gaps in coverage that kamikaze pilots could exploit. Morrison calculated fields of fire, ammunition supply requirements, and crew protection factors using slide rules and engineering tables, ensuring that the distributed defensive system would provide superior protection while requiring no more personnel or resources than traditional gun mount configurations. Captain Leslie Gers, commanding officer of the USS Franklin and a veteran of naval combat dating back to the First World War, initially viewed Morrison's proposal with deep skepticism that bordered on outright rejection. The distributed defense concept violated decades of established naval doctrine and required modifications to the Franklin that would take weeks to complete while the carrier remained in active combat operations. Gers had survived conventional naval warfare through adherence to proven tactics and tested equipment, and the idea that a single engineering officer could revolutionize defensive doctrine seemed not just unlikely, but potentially dangerous to ship safety and crew morale. But the kamikaze threat had reached crisis proportions that demanded extraordinary measures. Intelligence reports indicated that Japanese commanders were planning massive suicide attacks involving hundreds of aircraft that would overwhelm conventional defensive systems through sheer numerical superiority. Unless American naval forces could develop more effective countermeasures against kamikaze tactics, the planned invasion of Japan would face naval losses that could make the operation strategically impossible. Against his conservative instincts, and in direct violation of several naval regulations, Garris authorized Morrison to implement a limited test of the distributed defense system on the Franklin's starboard side, warning that any reduction in defensive effectiveness would result in immediate court-martial proceedings. Commander James Iron Mike Sullivan, the Franklin's gunnery officer and a veteran of every major Pacific theater engagement since Pearl Harbor, supervised the installation of Morrison's distributed defensive positions with professional skepticism tempered by desperate hope. Sullivan had watched too many good sailors die under kamikaze attacks that seemed to penetrate American defenses with supernatural accuracy, and he understood better than most senior officers that conventional anti-aircraft tactics were proving inadequate against an enemy willing to die with absolute certainty to achieve their objectives. The distributed defense system represented a fundamental departure from everything Sullivan had learned about naval gunnery, but the alternative was continued vulnerability to suicide attacks that were growing more sophisticated and deadly with each passing month. April 7, 1945, dawned clear and ominous as Japanese reconnaissance aircraft reported the Franklin's position to kamikaze squadrons preparing for what would become known as Operation Kikusui No. 6, the largest coordinated suicide attack in the history of naval warfare. Morrison's distributed defensive system had been operational for just 18 days, its effectiveness unproven under actual combat conditions. The modified gun positions looked strange and improvised compared to the geometric precision of traditional naval architecture, their scattered placement creating an asymmetrical defensive pattern that violated aesthetic principles naval architects had followed for generations. Japanese kamikaze pilots approaching the Franklin that morning expected to encounter the standard American defensive configuration they had been trained to exploit through months of tactical instruction and combat experience. Lieutenant Yukio Seki's successor pilots had refined their attack techniques to maximize damage against traditional gun mount placements, approaching from angles calculated to minimize exposure to defensive fire while positioning their aircraft for maximum destructive impact against ammunition storage areas and critical ship systems. The human guidance systems of kamikaze aircraft had evolved into precision weapons that could adapt to defensive measures and exploit tactical weaknesses with deadly effectiveness. But as the first wave of suicide aircraft approached the Franklin's defensive perimeter, something unprecedented occurred that would reshape Japanese tactical thinking about kamikaze operations. Morrison's distributed defensive system engaged the attacking aircraft with overlapping fields of fire that eliminated the approach corridors kamikaze pilots had been trained to exploit. Instead of concentrating defensive fire from predictable gun positions, the Franklin's modified defensive grid created a continuous wall of anti-aircraft fire that forced attacking pilots to maneuver through killing zones they had never encountered in previous operations. The mathematical precision of Morrison's defensive calculations became apparent as kamikaze aircraft found themselves unable to identify the single critical targets that had made their attacks so effective against conventionally defended vessels. The distributed gun positions provided mutual support that prevented any single successful impact from crippling the ship's overall defensive capability, while the overlapping fields of fire eliminated the geometric blind spots that Japanese pilots had learned to exploit through bitter combat experience. Lieutenant Hiroshi Tanaka, leading a 3-aircraft kamikaze formation in his modified Zero fighter, experienced the psychological impact of Morrison's defensive innovation as his carefully planned attack approach disintegrated under the continuous anti-aircraft fire from positions he could not identify or target effectively. The distributed defensive system created tactical confusion that prevented kamikaze pilots from making the calculated approach decisions that had made their attacks so devastatingly effective against previous American targets. Instead of engaging predictable gun positions that could be neutralized through precise impact placement, Tanaka found himself flying through defensive fire that seemed to come from everywhere and nowhere simultaneously. The Franklin's modified defensive system achieved something that American naval commanders had deemed impossible. It successfully repelled a coordinated kamikaze attack without suffering a single successful impact. Morrison's distributed gun positions destroyed or disabled 6 attacking aircraft, while suffering only minor damage to individual defensive positions that did not compromise the ship's overall defensive capability. The psychological impact on surviving Japanese pilots proved as significant as the tactical defeat, as kamikaze squadrons reported encountering defensive systems unlike anything they had been trained to attack. Word of the Franklin's successful defense against kamikaze attack spread rapidly through the Pacific Fleet as naval commanders recognized the strategic implications of Morrison's innovation. The distributed defensive system represented a fundamental breakthrough in anti-aircraft warfare that could potentially neutralize the kamikaze threat that had dominated American naval planning for months. Within weeks, technical specifications for the Morrison defense grid were being distributed to every major naval vessel in the Pacific theater under the highest security classifications available. The transformation of American naval defensive doctrine proceeded with unprecedented speed as the urgency of the kamikaze threat drove rapid implementation of Morrison's distributed system across hundreds of vessels. Shipyard workers from Pearl Harbor to San Francisco Bay worked around the clock to modify existing gun mounts and install new defensive positions according to Morrison's mathematical specifications. The aesthetic precision of traditional naval architecture gave way to functional effectiveness as American warships adopted the asymmetrical defensive configurations that had proven so effective against suicide attacks. Morrison's innovation represented more than tactical adaptation. It embodied the fundamental American approach to military challenges that emphasized practical solutions over theoretical perfection. Where Japanese kamikaze doctrine relied on fanatical determination and acceptance of certain death, American defensive innovation focused on systematic analysis of enemy tactics combined with creative engineering solutions that could neutralize tactical advantages through superior technology and mathematical precision. The distributed defense system demonstrated that democratic values of individual initiative and institutional flexibility could overcome even the most fanatical enemy tactics through applied intelligence and systematic innovation. The psychological impact on Japanese kamikaze pilots proved as devastating as the tactical advantages gained by American naval forces. Suicide squadrons that had approached American vessels with confidence born of months of successful attacks suddenly found themselves facing defensive systems that eliminated the tactical advantages they had been trained to exploit. The human guidance systems that made kamikaze attacks so effective became liabilities when confronted with distributed defensive fires that prevented pilots from identifying critical targets or executing planned attack approaches. Japanese naval commanders struggled to adapt kamikaze tactics to counter Morrison's distributed defensive system, but the fundamental mathematics of the innovation proved impossible to overcome through tactical modifications alone. The elimination of concentrated target areas and geometric blind spots that kamikaze pilots had learned to exploit created defensive effectiveness that could not be countered by increased pilot training, modified aircraft, or different approach techniques. The distributed defense system had fundamentally altered the tactical balance between offensive and defensive capabilities in naval warfare. By June 1945, as American forces prepared for the planned invasion of Japan, Morrison's distributed defensive system had been implemented across virtually every major naval vessel in the Pacific Fleet. The kamikaze threat that had dominated American naval planning for 8 months had been effectively neutralized through systematic application of engineering principles that eliminated the tactical advantages suicide attacks had previously enjoyed. Statistical analysis revealed that vessels equipped with distributed defensive systems suffered kamikaze hit rates below 3%, compared to the 25% hit rates that had made suicide attacks so devastatingly effective against conventionally defended ships. The strategic implications of Morrison's innovation extended far beyond immediate tactical advantages to reshape American planning for the final assault on Japan. Naval commanders who had calculated invasion casualties based on continued vulnerability to kamikaze attacks were able to revise their estimates dramatically downward, as distributed defensive systems proved capable of protecting invasion fleets from the massive suicide attacks Japanese commanders were planning to repel American landing forces. The Morrison defense grid had transformed what military planners had expected to be the bloodiest amphibious operation in history into a tactically manageable operation with acceptable casualty projections. Morrison himself remained largely unaware of the broader strategic implications of his defensive innovation, continuing his damage control duties aboard the Franklin, while modified American warships used his distributed defensive system to repel kamikaze attacks across thousands of miles of Pacific theater operations. The quiet naval engineer from Virginia had solved one of the war's most pressing tactical challenges through systematic analysis combined with creative application of mathematical principles, demonstrating that complex military problems could yield to individual innovation supported by institutional flexibility. The Japanese response to American distributed defensive systems revealed fundamental limitations in enemy tactical thinking that would prove decisive as the war approached its conclusion. Rather than developing new attack methods or modifying kamikaze tactics to address the changed defensive environment, Japanese commanders initially attributed their reduced success rates to pilot error, equipment malfunction, or temporary American tactical advantages that could be overcome through increased fanatical determination rather than systematic tactical adaptation. As summer 1945 progressed through the climactic battles for Okinawa and the preparations for Operation Downfall, Morrison's distributed defensive system continued to prove its effectiveness against increasingly desperate kamikaze attacks. Japanese suicide squadrons attempted to overwhelm American defenses through sheer numerical superiority, launching attacks involving hundreds of aircraft simultaneously, but the mathematical precision of distributed defensive fires proved capable of engaging multiple targets simultaneously without creating the vulnerability gaps that concentrated gun positions had always presented. The symbolic power of Morrison's innovation extended beyond its tactical effectiveness to represent core American values of individual initiative, technological innovation, and systematic problem-solving that characterize the democratic approach to military challenges. The distributed defensive system succeeded not through superior firepower or overwhelming numerical advantage, but through intelligent analysis of enemy tactics combined with creative engineering solutions that turned American industrial capability and mathematical precision into decisive tactical advantages. The recurring symbol throughout Morrison's story became the steady rhythm of the ship's bell, marking time through the endless hours of combat and modification work that transformed American naval defenses. That bronze bell, cast in peacetime, but serving through the crucible of global war, represented the continuity of American naval tradition adapted to meet unprecedented challenges through individual innovation and institutional flexibility. Each measured toll marked another moment of American perseverance, another increment of progress toward victory achieved through democratic values rather than fanatical sacrifice. The transformation of American naval warfare through Morrison's distributed defensive system demonstrated that technological superiority combined with creative tactical thinking could overcome even the most fanatical enemy determination. Japanese kamikaze pilots, who had approached American vessels with absolute certainty of death and confident expectation of tactical success, found their sacrifice rendered ineffective by mathematical precision and engineering innovation that eliminated the tactical advantages their attacks had previously enjoyed. August 15, 1945, exactly 5 months after Morrison first observed the geometric vulnerabilities that kamikaze attacks exploited so effectively, the naval engineer stood on the deck of the USS Franklin as news of Japanese surrender reached the Pacific Fleet through radio transmissions that officially ended the Second World War. The distributed defensive systems that had protected American naval forces from the kamikaze threat would no longer be needed for their original purpose, but their tactical innovations would influence naval architecture and defensive doctrine for generations to come. Morrison's distributed defense grid had played a crucial role in preserving American naval superiority during the war's final months, protecting the invasion fleets that would have carried American forces to the Japanese home islands if Operation Downfall had proceeded as planned. The psychological impact of effective kamikaze defense had also contributed to Japanese recognition that continued resistance was futile, as even their most fanatical weapons proved unable to inflict the casualties necessary to make American invasion too costly to pursue. As Morrison watched the sunset paint the Pacific sky in shades of gold and crimson, he understood that his technical innovation represented something far more significant than improved naval defensive capability. The distributed defense system had demonstrated that democratic values of individual initiative and systematic problem-solving could overcome totalitarian fanaticism through applied intelligence rather than matching sacrifice with sacrifice. In the contest between free societies and authoritarian regimes, the side that encouraged innovation and rewarded creative thinking would ultimately prevail through superior adaptation to changing circumstances. The lasting legacy of Morrison's innovation lay not merely in its immediate tactical success against kamikaze attacks, but in its demonstration that American military effectiveness derived from institutional flexibility that allowed solutions to emerge from any level of the command structure. A single naval engineer, given the freedom to analyze tactical problems and test innovative solutions, had fundamentally altered the nature of naval warfare through systematic application of mathematical principles and creative engineering. In the gathering darkness of victory, with the ship's bell marking the measured passage of time toward an uncertain but hopeful future, Morrison's distributed defensive system stood as testament to the power of individual innovation supported by democratic institutions. The bronze bell's steady rhythm had counted the hours through desperate combat and systematic innovation, marking time toward victory achieved not through superior fanaticism, but through the marriage of American values with technological capability that would define the post-war world. The distributed defensive positions that had protected American warships from kamikaze attacks represented more than tactical innovation. They embodied the fundamental truth that free societies possessed advantages that authoritarian regimes could never replicate or effectively counter. Morrison's system had succeeded because it emerged from individual creativity supported by institutional flexibility, demonstrating that democratic values of innovation and adaptation would ultimately prove superior to totalitarian reliance on fanatical sacrifice and rigid tactical doctrine. The solution came to him while examining damaged wing sections under the harsh fluorescent lights of the repair hangar. Morrison noticed that bullet holes created irregular patterns in the aluminum skin, and some aircraft had returned from missions with significantly less battle damage than others, despite flying identical routes. Careful analysis revealed that planes with more extensive surface irregularities, dents, patches, and makeshift repairs, seemed to suffer fewer radar-guided attacks. The correlation was subtle but undeniable. Smooth, pristine aircraft attracted more attention from Japanese interceptors than their battle-scarred counterparts. Morrison's breakthrough came from understanding that radar waves behaved like light, reflecting off surfaces at predictable angles. Standard American aircraft, with their smooth aluminum skin and geometric precision, created perfect reflective surfaces that bounced radar signals directly back to Japanese receivers. But irregular surfaces scattered those same signals in multiple directions, dramatically reducing the strength of reflected energy that reached enemy radar operators. The principle was simple enough for a Detroit mechanic to grasp, yet sophisticated enough to fool Japanese engineers who had designed their detection systems around conventional aircraft configurations. Working through the night of October 18th, Morrison began what would become known as the invincible modification. Using salvaged materials and improvised tools, he systematically altered the surface characteristics of a single P-38 Lightning, creating carefully calculated irregularities that would scatter radar energy without compromising structural integrity. Small metal triangles, torn from damaged aircraft and welded at precise angles, transformed the smooth fuselage into a complex geometric pattern. Wing surfaces received similar treatment, with tiny deflector plates positioned to break up the clean lines that Japanese radar operators had learned to recognize. The work required mathematical precision disguised as random damage. Each modification had to appear accidental while serving a specific purpose in the larger pattern of radar signature reduction. Morrison calculated angles and distances using slide rules and trigonometry tables, ensuring that scattered radar energy would disperse in directions that would not return strong signals to Japanese receivers. The modified aircraft looked like it had survived multiple combat encounters, its surface scarred and patched, but every mark served the calculated purpose of electromagnetic camouflage. Lieutenant Colonel James Dusty Rhodes, commanding officer of the 347th Fighter Group, initially viewed Morrison's project with skepticism bordering on hostility. Military regulations strictly controlled aircraft modifications, and the idea that an enlisted mechanic could solve problems that had stymied engineering officers seemed preposterous. But desperate circumstances demanded desperate measures, and American losses to radar-guided Japanese attacks had reached unsustainable levels. Against his better judgment, Rhodes authorized a single test flight with Morrison's modified P-38, warning that any structural failure would result in court-martial proceedings. Captain William Bill Mackenzie, a veteran pilot with 14 confirmed kills, volunteered to fly the modified aircraft on its maiden combat mission. Mackenzie had lost his wingman to a radar-guided attack just 5 days earlier and understood the strategic importance of Morrison's experiment better than most. The flight plan called for a reconnaissance mission over Japanese installations on New Georgia Island, following the exact route where previous American aircraft had been consistently intercepted. If Morrison's modifications worked, Mackenzie would reach the target area undetected. If they failed, he would likely join the growing list of American pilots missing in action over the Solomon Islands. October 22, 1942, dawned clear and humid, with visibility extending to the horizon in all directions. Mackenzie taxied Morrison's modified P-38 to the end of Henderson Field's coral runway, the irregular metal patches catching sunlight like scales on some prehistoric creature. Ground crew members watched with mixture of curiosity and concern as the scarred fighter accelerated down the runway, its Allison engines producing the distinctive sound that had earned the P-38 its Japanese nickname, Fork-tailed Devil. Within minutes, the aircraft disappeared into the vast Pacific sky, carrying with it the hopes of every American pilot who had ever faced the deadly accuracy of radar-guided Japanese interceptors. Japanese radar operators at Station Zebra 7 on New Georgia Island maintained their usual vigilance as Mackenzie's modified P-38 approached their detection range. Chief Petty Officer Yamamoto Kenji, a veteran operator with over 200 successful intercepts to his credit, monitored his screen with practiced attention, watching for the familiar electronic signatures that indicated approaching American aircraft. His Type A Mark II radar had never failed to detect enemy formations at maximum range, providing ample time for Zero fighters to climb to intercept altitude and position themselves for devastating attacks. But on this morning, something unprecedented occurred. Mackenzie's aircraft passed through the outer detection zone without triggering any response from Japanese radar systems. The modified P-38's scattered electromagnetic signature registered as background noise, indistinguishable from atmospheric interference or distant lightning strikes. Yamamoto checked his equipment twice, unable to understand why his normally reliable instruments showed empty skies when Japanese spotters reported hearing aircraft engines approaching from the southeast. For the first time since his assignment to radar duty, the veteran operator experienced the unsettling sensation of technological blindness. Mackenzie completed his reconnaissance mission without encountering a single Japanese interceptor, photographing enemy installations and troop movements with impunity while radar-guided Zero fighters remained on the ground, their pilots unaware that an American aircraft had penetrated deep into defended airspace. The modified P-38 returned to Henderson Field, carrying intelligence that would prove invaluable in planning future operations. But more importantly, it carried proof that Morrison's electromagnetic camouflage concept actually worked under combat conditions. The success of that initial mission sparked a transformation in American tactical, thinking that would ripple through every level of Pacific theater operations. Morrison's modification techniques were immediately classified under the highest security protocols, with technical specifications distributed only to selected maintenance personnel at forward air bases. Within weeks, entire squadrons of P-38s, P-51s, and P-47s had received the invisible treatment, their pristine aluminum surfaces transformed into complex patterns of calculated irregularity that confused Japanese radar operators across the Pacific. The psychological impact on Japanese air defense personnel proved as devastating as the tactical advantages gained by American forces. Radar operators who had spent months developing expertise in aircraft detection suddenly found their screens empty during periods when they could clearly hear approaching enemy formations. The reliability that had made Japanese radar-guided interception so deadly began to crumble as American aircraft seemed to appear and disappear at will, striking targets without warning and vanishing before defensive fighters could respond. Technical Sergeant Morrison's innovation represented more than clever engineering. It embodied the fundamental American approach to warfare that would ultimately prove decisive in the Pacific theater. Where Japanese military doctrine emphasized rigid adherence to proven techniques and standardized procedures, American forces demonstrated remarkable adaptability and willingness to embrace unconventional solutions. Morrison, working alone in a makeshift hangar with salvaged materials and improvised tools, had accomplished what entire Japanese engineering departments had failed to anticipate. The marriage of practical mechanical knowledge with theoretical understanding of electromagnetic principles. The Invisible Aircraft program expanded rapidly as word of its success spread through American air units across the Pacific. By December 1942, modified American fighters were conducting deep penetration missions over heavily defended Japanese strongholds, their radar-invisible configurations allowing unprecedented access to enemy territory. The strategic implications were enormous. American intelligence gathering improved dramatically as reconnaissance aircraft could operate without detection, while bombing missions achieved complete tactical surprise against targets that had previously been virtually impregnable. Morrison's workshop on Guadalcanal became an unlikely center of innovation as pilots and mechanics collaborated to refine the electromagnetic camouflage techniques. Each successful mission provided data that improved the modification process, and soon, American aircraft were disappearing from Japanese radar screens with such consistency that enemy commanders began questioning the reliability of their detection equipment. The psychological warfare aspect proved almost as valuable as the tactical advantages, as Japanese pilots lost confidence in their ground-controlled interception procedures. The transformation of American air operations in the Pacific Theater represented a fundamental shift in the balance of technological advantage. Japanese forces, which had dominated the early war years through superior tactics and equipment, suddenly found themselves facing an enemy that could strike without warning and disappear before retaliation became possible. The Invisible Aircraft program demonstrated how individual innovation, supported by institutional flexibility, could overcome seemingly insurmountable technical obstacles. By early 1943, Japanese military leadership had begun to recognize the scope of the problem they faced. Intercepted communications revealed growing frustration among enemy radar operators who reported consistent equipment failures and inability to track American formations that should have been easily detectable. Some Japanese commanders suspected sabotage or equipment malfunction, never imagining that American mechanics had discovered methods to render their aircraft electronically invisible through simple surface modifications. The strategic value of Morrison's discovery extended far beyond immediate tactical advantages. American bombing campaigns against Japanese industrial targets became exponentially more effective as B-24 and B-25 formations could approach heavily defended objectives without triggering radar-guided defensive responses. The systematic destruction of Japanese manufacturing capacity accelerated dramatically as invisible American bombers struck with impunity against targets that enemy commanders believed were adequately protected by sophisticated radar networks. As 1943 progressed, the cumulative impact of invisible American aircraft operations began to reshape the entire strategic situation in the Pacific Theater. Japanese air defenses, designed around radar-guided interception techniques, became increasingly ineffective against modified American formations that could penetrate defended airspace without warning. The psychological impact on enemy pilots proved as devastating as the material losses inflicted by surprise attacks, as Japanese aviators lost confidence in ground-controlled interception procedures that no longer provided reliable early warning. By mid-1943, Japanese military leadership had begun to comprehend the scope of the challenge they faced from invisible American aircraft. Emergency conferences convened to address the radar detection crisis, but Japanese engineers proved unable to develop effective countermeasures against American electromagnetic camouflage techniques. The technological advantage that had served Japanese forces so well in the early war years had been neutralized by a Detroit mechanic working with salvaged materials in a Pacific Island hangar. The Invisible Aircraft program's impact extended beyond immediate military applications to influence post-war aviation development. Morrison's surface modification techniques provided the theoretical foundation for stealth technology that would revolutionize military aviation in subsequent decades. The principle of scattering radar energy through irregular surface configurations became a cornerstone of advanced aircraft design, demonstrating how wartime innovations could have lasting implications for technological development. Morrison's story embodied fundamental truths about American military effectiveness that extended far beyond individual tactical innovations. The Invisible Aircraft program succeeded because it combined practical engineering knowledge with institutional flexibility, allowing innovative solutions to emerge from unexpected sources. A Detroit assembly line worker, given the freedom to experiment and the resources to test his ideas, had solved a problem that challenged the most sophisticated military engineers of his era. The psychological transformation of American air operations in the Pacific Theater reflected broader changes in military confidence and tactical thinking. Pilots who had previously approached heavily defended targets with understandable apprehension now flew their invisible aircraft with renewed confidence, knowing that Japanese radar systems could not provide early warning of their approach. This shift in pilot morale translated directly into improved operational effectiveness as American air crews pressed home attacks with determination born of technological advantage.